good afternoon.
Hello.
Hello. All right, so we're going to continue from yesterday. Yesterday was story time, where we started talking about this dude named Pythagoras and his right triangles. Okay? Some of you already did a title and header yesterday. A lot of you didn't, and that's okay because you didn't have to write notes yesterday. It was just story time. So if you didn't write the title for yesterday, please make sure you do so now. If you did write the title yesterday, you must make sure to get the new objectives today. So we're still looking at right triangles, and we'll be looking at right triangles for a few weeks. The rest of the 6 weeks, that's for certain. Today we will be classifying triangles. Do you remember some of your triangle classifications? Equilateral. Isosceles. Right.
Acute.
Acute.
I did that.
Obtuse.
I did that too.
Yeah, all of these are triangle classifications. Some are side classifications, like equilateral, isosceles, scalene. Some of them are angle classifications, like right, acute, obtuse. We will be classifying by angles, but I'm not going to give you any information about the angle measures. I know, right? What? How are you going to do that? What? Here's how. I'll wait. So I'm not going to be giving you any information about the angle measures. So in order to classify them, we're going to be using the Pythagorean Theorem. What do you need to? Oh, okay. I'll move my hand. So we're going to start today with the Pythagorean Theorem. When I say Pythagorean Theorem, what do you think of?
Pythagoras.
Yep.
Okay.
Do you remember the formula?
Nope.
A squared plus B squared equals C squared. Yep, that is the formula for the Pythagorean Theorem. What I want to start with today is the actual theorem itself. Something a lot closer to that wordy thing that Pythagoras had said originally. Can I get rid of the headers on the right?
Yeah.
Okay, here we go. It says, if a triangle is a right triangle, then A squared plus B squared equals C squared. This statement requires us to start with a right triangle, and if we don't start with a right triangle, we can't use this. Let's clarify what A, B, and C are first real quick. We're going to have A and B be the legs of the triangle. And we're going to have C be the hypotenuse. That is the longest leg of the right triangle. It's right across from the 90-degree angle. But miss, you ask.
But miss.
The hypotenuse. Legs. A and B are legs of the triangle. But miss, you ask.
But miss.
How does this help me classify my triangle? I have to know it's a right triangle before I can use this. How does this help me say whether it's a right triangle or not? And my answer is, dude, you're right, it doesn't. So we're going to take the converse of it, because when we flip the hypothesis and conclusion from our conditional statement days, we take the converse, we end up with something that will, in fact, classify our triangles for us. So this is the converse of the Pythagorean theorem. Now recall, when you take the converse of an if-then statement, you're going to take the second half of the stuff and write it first. Okay? So if, now this says if C is the hypotenuse. But I can't say it's the hypotenuse yet because I don't know this is a right triangle. Hypotenuses are only for right triangles. So the most I could say is that C is the longest side. So if C is the longest side of a triangle, and A and B are the other two sides, and there's a lot of conditions on this one. A squared plus B squared equals C squared. If I have all of that, then I can say I have a right triangle. Let's do a quick example. When you're ready, draw a triangle. Any triangle. It doesn't have to look like a right triangle.
Yeah.
You just get in there, go ham, triangle. Bam. All right, name the triangle, 3 points, go.
ABC.
J.
I tried to grab from 3 different voices. All right, now I need the links of the sides of these triangles. So 3 numbers, go.
1, 2, 3.
14.
Damn.
All right. And the question is triangle ABJ a right triangle? Some say yes, some say no. There's only one way to find out. Go into the Pythagorean Theorem and see if we get a true statement out at the end. All right, so we need to figure out which is the longest side.
14.
Yeah, the side with the 14. It's got the biggest number. There's C. Mark the other 2 as A and B. No one cares which one you mark as A or B. Okay, you mark them however you want. You make it happy for yourself. Thank you. All right, now we're going to substitute. A is 11, B is 1, and C is 14. You might need calculators, I'm just saying. Your pocket calculators work just as well. Adia's like, I've got one on my desk. Yes. All right, 11 squared is
121.
121. 1 squared is
1.
14 squared is
Oh, it's not 196?
196.
Or no?
She's saying 196. Someone confirm?
Wrong.
It is.
122.
Yep, she confirmed it, and he double confirmed. Nice job. Good memory.
Wait, what? Isn't that a 1 2 1?
Where?
1 times 1 is 1.
This
right
one.
there.
This right here?
Yeah.
Yes, it's 121.
Plus 1?
Yes.
Then why is it 196?
The 14 square.
14 squared.
Oh, okay.
All right, so is 122 the same as 196?
No.
Yeah, no. So, hey, ladies. So no, there's no way that this triangle ABJ is a right triangle. He's like, I was right. I did it. Yeah, you're right. But this still doesn't help us classify. This only tells us right triangle, not right triangle. It doesn't tell us if we have an acute or an obtuse or an equiangular. We don't know yet. For that, we need the help of 2 corollaries. Recall that a corollary, whoops, I don't know why I'm writing in red. A corollary is a statement that comes from immediately after, like the result of some other statement. So these two statements are the result of the thing we just looked at in the converse of the Pythagorean theorem. Here's the first one. If C is the longest side, and A and B are the other sides of a triangle, notice our setup is exactly like the converse, and A squared plus B squared is less than C squared. Not equal to this time. But if it's less than, then the triangle that we were looking at is not a right triangle, but is actually an obtuse triangle. Let's get the second corollary in very quickly. We're going to have the same setup. We want C being the longest side. We want A and B to be the other sides. We want this to be of a triangle, not a circle, because that would be weird. But this time we want that Pythagorean theorem result to be greater than C squared. When that happens, our triangle is an acute triangle. So look at the example above. What kind of triangle did we make?
Obtuse.
Yeah, we made an obtuse triangle. Because this information here, our A squared plus B squared, was less than our C squared. You see it? Okay. I'm out of room on this page. I need to go to the next. You can get the next example in like 3 lines or less. So if you have 3 lines left on your paper, definitely stay here and continue. But I need to go to the next page. I'll flip in about 10 seconds. Bless you. That was 6 seconds. I'm sorry. I lost count. And I was like, well, I guess I should better just turn the page now because I lost count and people look bored. All right, so here's our example. We're going to do one more example of the previous. The example says, classify the angle, or the triangle. Can I have 3 numbers? Go.
11, 16, 17.
25.
21. 16.
21. Okay. And that's all you're given. Those are the side lengths of your triangle. Which one is playing the part of C?
25.
The 25 because it is the biggest. And no one cares the orders of the other 2. So there's A and there's B. All right, we're going to run them through the Pythagorean theorem again. A squared plus B squared. But this time I'm going to put a box there because I don't know what the relationship is going to be. I don't know if it's going to be less than or equal to or greater than. So I'm going to leave a box there like we used to do in kindergarten. We were learning to compare numbers. Remember doing that? Yeah?
Nope.
All right. Nope. Let's fill in. Here's A. Here's B. And here's C. I can do 11 squared in my head, but I need help with the others. What's 21 squared? 441.
Yep.
All right, confirmed. And 25 squared. I think it's in the 600s. 625. I heard that from two people. All right, add 121 and 441. Do it any way you want. I'm going to try to do it
653.
653? 221 and 441. 562. Okay, that's what I was starting to write, and then I got. All right, so compare 562 with 625. Less than, greater than, or equal to?
Less than.
It's less than. So what kind of triangle do we have?
Obtuse.
Obtuse again. All right, make sense? All right. That was one day.
Yay!
Okay, shake out your hands.
That was quick.
Shake your hands. All right, let's do day 2. Ready? Oops. Ignore that. Ignore that. All right. Bless you.
Thank you.
So we looked at using this Pythagorean theorem thing to help us classify triangles as whether they're acute or obtuse or right triangles. But remember, the one big thing about Pythagoras was that he wanted whole number ratios.
And no beans.
Yeah, no beans. Whole number ratios. He did not want numbers that you couldn't write as a fraction between two whole numbers. He didn't want them at all. Okay? So whenever we encounter 3 whole numbers, which we call integers, whenever we encounter 3 integers that satisfy the Pythagorean theorem, that means they make it true, unlike the example we just did, then this set of 3 numbers has a special name. These 3 whole numbers, these 3 integers that make the Pythagorean theorem true are called Pythagorean triples. They're like triplets. I would like you to make, please, a table in your notes. Give me a title where you're going to write triples here. And then make it 4 rows big after the title. So you're going to have a table that looks something like this. Now, I really, really, really want you to memorize the first 2 triples for sure, because they're going to come up time and time again on those college entrance exams. So if you're getting ready to start looking at that, if you're looking to try the TSI, okay, if you are, this is going to come up for you. When you move on to what math apps, some of you have it this year, some are going to take it next year. Algebra 2, you're either going to take next year or are currently taking or are going to have next year. These triples are going to come in handy, okay? The first triple is 3, 4, 5. These 3 whole numbers, when the biggest is playing part of C, make the Pythagorean theorem true. Try it real quick. Take 3, square it, add it to 4 after you've squared it. So go 3 squared plus 4 squared. Hit enter. What do you get? 9 plus 16? 25?
Mm-hmm.
What's 5 squared?
25.
It worked. Pythagorean theorem, right? Which means that I could hand you a question that says, you have this right triangle, the legs are 3 and 4. What's the hypotenuse? Say it. 5. Here are the legs. There's the hypotenuse. You don't have to do the Pythagorean theorem again. It's a waste of time. Don't do it. you got the Pythagorean triples memorized, boom, gives you your answer every time. But if only tests, tests aren't always that simple. Test writers want to try to trick you to make sure that you know what it is that you're doing. And so what they're going to do is they're going to make use of scale factors. Remember, scale factors are those numbers that you multiply to the length of polygons to make them bigger or smaller. To create those similar polygons, to make dilations. All of those things meant the same thing, by the way. So if I took this Pythagorean triangle and I applied a scale factor of 2, what would be my new side measurements? 6. Yep. Yep. Whoops. So, we saw it at the same time. Thank you. I heard you go, wait, and I was like, oh. Whoops. All right, they might also hand you this one. I've seen this one a couple times. What happened there? We multiplied by 3. So our scale factor for that particular triangle is 3. Here's another Pythagorean triple that I really want you to memorize because I've seen it come up a lot. 5, 12, 13. There are more. There are a bunch more. Like hundreds more. And so, your notebook check, another quick 100 grade for you, which I would like to see by Friday. You should have time after lecture to start on it. I would like you to please complete the table.
So we have the 2.
But miss, you didn't give me 2 Pythagorean triples. I know. You have to go find some.
Oh, come on.
Make up some numbers. Run them through the Pythagorean theorem. If you get things equaling each other, like you did with the 3, 4, 5, it's a Pythagorean triple and you can add it here. Then give me scale factors of 2 and 3. There's one catch. You may not, under triples, you may not give me things that are scale factors of the other 2. So please don't give me 30, 40, 50. Because that's just 3, 4, 5 with a scale factor of 10. Okay? I want a brand new Pythagorean triple. All right? All right. By the end of class on Friday, please. Okay? So you have 2 days to finish this out. All right. Let's step away from hard Pythagorean theorem. We're still going to use it. But let's start on something kind of new. Still dealing with right triangles, mind you. But I want to give you some special cases. Okay? Some ways that if you were told just a little bit of information, including angle measurements, bless you, you're able to calculate the measures of the sides of these triangles. I have 2 kinds, so I'm going to split my working space down the middle this way, leaving you this entire left-hand side for scratch work or whatever you might need. Okay? The first one is called the 45-45-90 triangle. Those of you who are looking on my notes from a previous class saw this in a slightly different format. I want this format for you. I think it's going to be stronger. Okay? And it looks like this. Check it out. It's a triangle like this. We have a right angle here. This angle is 45 degrees. This angle is 45 degrees. And these 2 legs are congruent to each other. Bam. 45, 45, 90. But there's something special about how the Pythagorean theorem works with the legs of this triangle. In fact, this triangle is that special case that Pythagoras got really upset about. Remember? The case where the right triangle, where the legs were both the same size. Yeah, they were equal.
He killed someone because
Yeah, he killed someone because of this triangle. We're going to unlock that secret, and we're not going to be scared about it or kill people, because killing people is bad. Let's not. Yeah, let's not. Here's the pattern. All you have to do literally is just memorize this pattern. Whatever the measure of this side is, I don't care what the number is, it's going to be the same as this side. They're going to have the same number. And then this diagonal, the hypotenuse, is going to be that same number times the square root of 2. Times the square root of 2.
yeah.
Let's experiment. Let's see that this works. All right? So, if x is, please give me a small number, not 1.
7, 2.
So let's take 3.
Damn.
Not that I don't like 7, but the numbers get really big really fast with 7, and I don't want to go there. So let's do 3. Okay, so if x is 3, we're going to do the formula for the Pythagorean Theorem. A squared plus b squared equals c squared. Okay, a and b are my legs, so we're going to have 3 squared plus 3 squared, and that's going to equal, I'm going to leave it as c squared because what I'm looking for is a pattern that looks like this. When I'm done, I want my answer for c to be 3 times the square root of 2. That's what I'm looking for, okay? All right. There's 9, and so c squared is 18, and so c is the square root of 18. And you're going, miss, that ain't the 3 square roots of 2. But you got to simplify it. You remember way back towards the beginning of the year, we were simplifying radicals?
Yes.
And then we did it again when we had to do distance formula? And then we did it again in one of the assignments that you're working on right now? Yeah, we get to do it again. We're practicing it. All right. What are the factors of 18?
19, 19.
2 and 9. 3 and 6. I think that's all of them. All right. Is 2 a perfect square?
No.
Meaning that it's got a whole number square root? No. Does 9 have a whole number square root?
Yes.
Yes. So this is the pair I'm going to use. I'm going to rewrite the square root of 18 as the square root of 9 times 2. You remember doing that?
Yeah.
Yeah? You remember doing this? Then I can break that radical right at the multiplication and rewrite this as the square root of 9 times the square root of 2. What's the square root of 9? 3 times the square root of 2. It is now in the same format. If you think this is witchcraft and it was just because I picked the number 3, I urge you to go back on a scratch sheet of paper or over here on the left-hand side where you have some extra writing space and do it again with any of those other numbers that we did not select right now.
Witchcraft?
Yeah?
I will cross.
Okay? And it should, once you're done simplifying it, you should be able to get back to this form, okay? All right. Let's do the very last special triangle for the day. The last item for the day, and we've got about 15 minutes left. 18. Thank you for being on top of it. All right, here we go. 18 minutes, one problem exactly like this. You ready?
Yeah.
Let's do this. The next special right triangle is called the 30, 60, 90 right triangle, and it's called that because it looks like this. This tiny angle right in here measures 30 degrees.
Wow.
This medium angle right here measures 60 degrees. And the other one is 90 degrees. Like the 45, 45, 90, its sides too have a special proportion that they come in. This set pattern that will always happen when you have a triangle with degree 30, 60, and 90. Bless you.
Thank you.
The pattern is this. whatever the measure of the short side is, the hypotenuse is going to be 2 times that. And then the medium side, the one across from the 60, is going to be that number times the square root of 3. Again, the radicals that Pythagoras doesn't like. Again, let's confirm it. Can I please have a small number for x, not 1? 2. I heard 2.
5.
You're welcome to try it with those numbers. Okay, they just get a little bigger. All right, here we go. We're going to do the exact same process. A squared plus b squared equals c squared. Yeah. A is going to be x, which is 2. B will be the other one, which is going to be 2 times the square root of 3. And then I'm going to leave c squared by itself. Okay? Because what I want at the end is for me to have a value of c that is 2 times whatever our value for x was. So 4. I want c to be 4 at the end. All right, here we go. So 2 squared is 4, and oh, sweet mother of... Let me show you how to handle this. It's really not that bad. Are you ready for this?
Calculator.
Do you see how there's no operation between those two numbers?
Yeah.
So there's this invisible multiplication between them. Please notice how badly I'm going to stress this next phrase.
6.
Whenever you have things with multiplication raised to powers, you may distribute the power, but only when it's multiplication. Not addition, not subtraction, not division, just multiplication. Okay? And I'm stressing that because when you hit Algebra 2, you're going to have a huge section on this. They're going to mix up the addition, subtractions, and multiplications on you, and you have to be able to know which one to do when. Distribute only when there is a multiplication. Got it? All right. So then, this becomes 2 squared, and this becomes the square root of 3 squared. All right, it looks a little messy, but I'm showing you that we just distributed that power. 2 squared is 4, and now I have a square root being raised to a square power. Roots and powers are opposites, the same way addition and subtraction are opposites. They cancel each other out. Since these have the same type, they're both square things, they cancel completely. All we're left is the stuff inside the casita, the radicand. The little casita. Looks like a little house. The radical. All right, we're almost done. 4 times 3 is 12. 4 plus 12 is?
16.
And what's the square root of 16?
4. What? Yes.
4 times 4 is 16. The square root of 16 is 4.
Times 2.
This 4 can be written as 2 times 2, which is the exact same format as that. Questions on anything you saw today?
No.
All right.
What's the answer for the other one?
For which?
490. The 45, 45.
This one?
Okay.
See how they look the same? Yeah. This is like a cookie cutter. Now you can put any numbers in there and boom, you get it. What happened to the 4? Question? That's a plus. It's not a 4. It does look like a 4. It's a plus. I'm sorry, my bad handwriting. It's a plus. Fix your notes. That's not a 4. It's a plus.
What's a plus?
It's a plus, not a 4. Uh-oh. Fix it. It's a plus. All right. Thank you very much.